Thank you for inviting me. So my name is Nikolaj Van Omme. I'm the CEO of a small company doing AI differently, Funartech. And today I'm going to talk about what we think is the future of AI. Actually, one part of what we are doing since a few years is becoming mainstream this year. What is important to know about me is the fact that I have been doing different things. So I'm a pure mathematician. I'm also an applied mathematician. I'm not an engineer, but I have a degree in engineering. I did industrial engineering. I'm also a computer scientist. So that's important to know that I like to mix things, because this is exactly what I'm going to present. So Funartech, we decided in 30 minutes to find a name for the company. And basically, if I tell you what it's all about, you will never ever forget about it. So it's fun, art, tech. So we work a lot. So hopefully it's fun. We describe ourselves as artists. And then obviously we are in tech. So fun, art, tech. So tonight I'm going to talk about the hybridization of ML and OR. OR is operations research or operational research. By the way, who knows a little bit or knows about OR? Wow! A lot of people, great. So what we are doing is combining ML, machine learning, and OR. From now on, when I say ML, it's machine learning, OR, operations research. So why do we think it's the AI of tomorrow? Well, the thing is, we have better practical and theoretical results. So that's a good hint that it might be something useful. Also, we get more and more traction, or that idea gets more and more traction. And as I said, one of the ways to combine ML and OR became mainstream this year. So when I'm talking about hybridization of ML and OR, I'm really talking about a complete hybridization of both. We have new algorithms. Basically, you can combine ML and OR in 4 ways. The first one, which is becoming mainstream this year, is to combine ML and OR as black boxes. So you use one and you use the other, but separately. And most of the time you use first ML to predict, and then you use OR on those predictions to optimize. So you can also use one to improve the other. So you can use ML to improve OR. Works very well. You can also use OR to improve ML. Actually, this is what ML is. Because OR, I'm going to talk a little bit more about OR in a few seconds, but OR is basically the science of optimization. Whenever you talk about optimizing something, I want to minimize, I want to maximize something, actually there is a science behind this, and it's OR, operation research. So ML is basically using operation research to optimize its prediction. And then there is this new way of doing things, a total complete hybridization of both, where we have new algorithms. And I'm going to show you 2 examples of things you can do with that hybridization. So, more and more traction, yes. Well, I'm going to use the mouse. So, in November 2018, so I have 3 examples here, but there are lots more. Machine learning for combinatorial optimization, a methodological tour d'horizon from Joshua Bengio, Andrea Lodi, and Antoine Prouveau. I guess you know at least the first one. So this is a review, and this is the conclusion. And in the conclusion, I'm going to read, we believe end-to-end machine learning approaches to combinatorial optimization are not enough, and advocate for using machine learning in combination with current combinatorial optimization algorithms to blah, blah, blah. Combinatorial optimization is OR. So in that article, they say, literally, use ML and OR for combinatorial problems. June 2019, Scale AI, one of the 5 big clusters in Canada. Scale AI is now calling for projects that combine machine learning, operational research, again OR, and data science that can be applied to supply chain. Ourselves, Funartech, in January 2020, we're going to start 2 fundamental research projects at École Polytechnique, and we're going to start an applied project at McGill. There are lots of other examples of that. The combination of ML and OR is really becoming mainstream. By the way, I don't know if you noticed, on the 6th presentation today, there are 3 proposing to combine ML with something else. And actually, that's the future. Because ML is great, but if you combine it with something else, you have even better results. So that's the big picture in general when you talk about artificial intelligence. So you have artificial intelligence, and inside artificial intelligence you have machine learning, and within machine learning you have deep learning. That's the picture we usually see. In fact, there are some candidates missing, and in particular there's this one missing. It's OR. Actually, all those fields are based also on OR, up to a point. So what is OR? So as I said, it's the science of optimization. How do we use OR? Well, basically it's always the same way to do things. We have a real problem, like here we have the problem of crossing bridges in a city. So we have 7 bridges, so it's a real problem. I'm gonna talk about it a little bit later. And then we modelize that problem into a mathematical model. We solve that mathematical model mathematically. We find mathematical solutions, and then you try to translate those solutions back into reality to be able to take a decision. By the way, if you know prescriptive analysis, this is done mostly by OR, while ML is doing predictive analysis. So here, for instance, you have 7 bridges in a city called Kaliningrad. Now it's it's now Kaliningrad. It was Königsberg before. And the question is it possible to do a tour by crossing each bridge only once? One way to solve that problem is to modelize this into a graph where actually a bridge is replaced by an edge. So the question now becomes, can I do a tour in this graph by crossing each edge only once? By the way, this is a graph. Graph theory is part of OR. The solution is no, it's not possible. So there is another question. Okay, I need absolutely to cross a bridge at least twice. How many bridges do I need to cross minimally to be able to do the tour? The answer is 2. We can prove this mathematically. Here you have a solution. And then in this case, it's quite easy to translate that solution back into reality. But most of the time, doing that translation back is not that easy. So that's basically what we do in OR. Some results. We get often, not all the time, but we get often 20–40% of improvement. This is huge. In the case we don't, and we only get, I don't know, 0.1% of improvement, it can still be worth it. For instance, if you can minimize the pollution on Earth by 0.1%, it might be worth. It's already used extensively in a lot of sectors: transportation, internet, army, supply chain, and others. And as I said, optimization, OR, is the science of optimization. Quick comparison between OR and ML, just to show off OR. So on the right, you have the TSP. TSP is the traveling salesman problem. That's a problem where you have cities and you want to do a tour, visiting each city only once. And you want to come back and you want to do this for a minimal amount of effort, like for instance, a minimal distance, minimal time, something like that. It's an NP-hard problem. People in ML try to solve that problem, and they can solve it today up to 100 nodes, which is great. But look at what OR is able to do. OR is able to solve this with 100,000 nodes. Again, this is an NP-hard problem. So going from 100 nodes to 200 nodes is already very difficult. Imagine the gap between the two. On the left, you see a column where I'm writing that most building blocks of ML are coming from OR, like gradient descent. Gradient descent is coming from OR. Even backpropagation is coming from OR. Boltzmann equations, OR, etc. Now, an example on how to combine them both. This is becoming mainstream this year. So you use them both separately. So let's say you are a train company and you want to replace your tracks. How can you do this for a minimal cost? One way to do this is in 2 steps. First step, you use deep learning. So you put cameras under your wagons, you let your train go, you take pictures in quick successions. With deep learning, you're gonna stitch those pictures, and with deep learning, you're gonna be able to say, oh, I need to replace that track in 3 months, this one in 6 months, this one in 2 years, these ones need to be repaired, and things like that. You have a mapping of what you need to do, but you don't know how to do it. Because you can send a team to replace a track, but maybe that same team should also replace or repair another track next to it, even though it shouldn't be repaired right now, maybe in 6 months or 2 years, but it would cost less to do it right away than to send again another team later on. This is what OR can do. It can optimize that. So that's the perfect combination of OR and ML. So with ML, you have predictions. With OR, you can optimize on those predictions. And time is flying by. That's an example we did at Funartech. So we had a restaurant chain that asked us to optimize their booking system. So before we came, they wanted, the way they did it was to have someone calling them, and then they said, okay, what do you need? Well, I'm coming at 6, I need a table for 4, and then you guess that because there are 4, they're gonna stay for 2 hours. It's a very stochastic problem because actually they came only 3, only 3 of them, and instead of coming at 6, they came at 6:20, for instance, and they didn't stay for 2 hours, but for 4 hours. So basically, before we did anything, what happened was the assignment was done and fixed once and for all. That's suboptimal, because it can happen that you are assigning a table of 8 to a group of 5. And if you don't change that, maybe later on this is going to be a group of 6 and they will not be able to come because that table is already occupied. So just to tell you that we combined ML and OR. So ML, well, you can optimize, estimate eating times, when they are eating, when they are booking, and things like that. We also built a recommendation system telling them, okay, maybe you shouldn't accept a booking even if that booking is possible, because there is another one coming after, or maybe there was someone coming at the door without reservation, and you would not be able to accept that group if you accept that booking. And then we used OR to optimize the overall assignment of tables. We got 20% of improvement. That's huge. And by the way, I'm also very proud that we could do this system under 3 milliseconds. The system was reacting under 3 milliseconds. I had something very interesting about the constraints, but the thing is, I only have a few minutes left, and I would like to talk about the total hybridization. First of all, this is another problem where we use ML and OR like 2 black boxes. So this is typically a computer vision project where we want to recognize sausages. Just to say that if you use deep learning, it works not that very well because we had a 2D camera, not a 3D. And people were manipulating the sausages. So when you had a sausage and you put another sausage in front of it, the system is totally lost. So deep learning is not working very well. So what we did was to use ML, yes, deep learning, and also OR. And actually, we had much better results, but I don't have time to go over that one. Here, I want to take some time about those 2 projects. So I'm talking about a total hybridization of both. So we have new algorithms. One first project is about injecting emotions into AI. So we are not doing sentiment analysis, we are making the bots emotive, making them angry, happy, empathic, whatever. If you are trying to do this only with ML, there are lots of problems that are popping up. Here I listed 4. There are many, maybe not many more, but there are some other problems. So first of all, you need a lot of data. Emotions are really contextual. You need a lot of data. You also have data that will be biased because emotion is really hard to get right data. Then the system cannot change automatically its emotion. It's really hard. You need data about changing emotion. Already having that data about emotion is hard, but about changing emotion is even harder. Also, another problem is that such system cannot be controlled. Your system can be totally going berserk. Why am I listing this? It's because we have a solution for that with OR, by combining OR and ML. So if we have data, we use it. We don't need a lot of data. About biases, we have solutions. Our system can change its emotion autonomously. And it's totally controlled in the sense that it cannot go berserk. Another project that is even crazier, it's what we call an open door towards AGI. So we don't have AGI, but we have something that maybe might lead to AGI. What we have is the first really truly intelligent algorithm. So when I'm saying this, it's because we are not mimicking the brain. This is way too difficult. We don't believe that we know enough about the brain how it's working. So what we do is trying to have a system that that you would like to call intelligent. So we have a system that is able to autonomously change its perception, its learning, its vision of its surrounding in a way that it can improve it, and also that it can totally get rid of what you are giving it at the beginning. So it can erase completely what you're giving the system. We would like to call this intelligence. We claim that we have this. Not that we think we know how to get there, no. We claim that we have this. The other problem, we already have code. This one we don't. This one we're going to start January 2020 at Polytechnic. But the thing is, we believe that we can make this work not tomorrow, but maybe after tomorrow. So that's something you can do with the combination, the hybridization of ML and OR. And this is our roadmap. No idea if we get to AGI, but at least we might get to this intelligent system. So for the moment, we are a little bit late. If you look at Q1, Q2, so we did a POC for the emotions into AI. We did an MVP. We showed it. But we are late on the POC, the third step. But anyway, we hopefully will get there somehow. And that's it. Thank you very much. Questions?
Thank you for the talk. What's the technology behind your system? You call it optimization. Did you use simplex, OPL?
We could have used simplex, but we don't because it's too costly for us. But yes, we use such tools. If that's the question, yes, we do.
I just saw such example. It's perfect.
Yes.
So how flexible is what you did for changing to another task that is like vision and you have to keep track of this? What is the degree of freedom you have for?
It's extremely flexible. Actually, I truly believe that you can apply this to anything.
Anything is
Anything. I'm doing this since 25 years. I didn't see a single example where it didn't apply.
What about robotic optimization?
Yes.
So thank you so much for your presentation. I'm interested about part of emotions.
Mm-hmm.
You said it's kind of hard to do it using ML. How would this be possible with OR? I know because I worked in this field. The main issue we had was about getting training data for ML.
Mm-hmm.
And what we did, we tried to kind of go around and use some kind of hard code, I'll say. It wasn't really a data set. There's some kind of research existing. I mean, some other universities did collect their own labeled data, like they write some text, like novels, imaginative, and put a label about angry,
Mm-hmm.
that kind of.
Yes.
Well, that's the main issue for me. Otherwise, it's easy. If we have labeled data, machine learning will do great using NLP.
Yes, except that you need data that is huge. I mean, you need more data than there are atoms in the universe. I would say if you have all the data, then all the problems are solved, and then machine learning is working pretty well. Yes, but this is not the case, and it will never be the case.
I didn't try this. What about reinforcement learning?
We are also using reinforcement learning, but not only. So the key is to use all those tools and to put them together. If you know the advantages and disadvantages of all the tools and you know how to combine them so that you can combine the advantages, you go way further.
You didn't give us more details.
No, I didn't, because this is proprietary.
Okay.
Yes.
I thought this was...
No, and the thing is, a few years ago, I came and I knocked on doors, and I was a crazy guy. No one believed me. So I have a company now, and I'm building it and I'm selling it. And then next year we're gonna go back to university, and probably we're gonna give some back, and we will write some articles. But for the moment, no, it's proprietary.
Thanks for the presentation. You mentioned that your system autonomously changes emotions
Yes.
and doesn't get berserk, and you
Yes.
said it's controlled.
Yes.
So is the control external or is it built into the system? That's the first part of the question.
What do you mean by external? I mean, it's inside the system, but I mean, I would like to know what you would.
So you say that a system is at a particular emotion.
Yes.
Let's say it's a chatbot, to
Mhm.
make it simple. So there's an angry customer, and
Yes.
there's this chatbot that is assimilating, it is sensing that the customer is angry. And it would possibly react in a way that a customer representative would, a human customer representative, if it is to emulate a human customer representative, it would possibly first try to understand what is the source of the problem and try to address the root cause of the problem, right?
Mm-hmm.
And in course of it, you are programming submissive states into the system. Is that right? You have to.
Yes,
You
but
cannot
I mean,
nail that as
we
a
are
customer.
we're combining all those tools.
Right. So you move from one state to the other state, and it is more submissive in nature, and you transition between them. So my interest is in understanding what is the basis of, or what is the training data. I know most of what you're doing is proprietary, so I wouldn't go there.
So actually, I'm gonna give you something more. Our system can also find out by itself what emotion is. Not in the sense that it knows what an emotion is, but it detects what an emotion looks like and how to mimic it. We have no idea what an emotion is, but we mimic emotions. What was your question again? Sorry.
So how do you say that you are moving between
Okay.
emotions?
Well, how can I explain this without giving too much away? I would say that if you are interested, let's talk. But probably if I say too much, then, I mean, there are lots of clever people here in the room, and what we do is not that exceptional. I mean,
Okay, probably I look forward to your academic project. Thank you.
So one last question here.
Yes, thank you for the presentation. Well, I think we read everywhere about promising applications of artificial intelligence, but very little about operations research. And I think I agree with you that in the future these two fields need to be merged. Also because my background is also in operations research.
okay.
But probably I would like to know what do you think are the main challenges or limitations, at least at the moment, for this integration? Why this is not so widely understood?
If I had a lawyer, I would say I need to talk to my lawyer before I can say anything. I think there are reasons, not good ones, but I don't think it would be clever for me to say it openly. So if you want to have that discussion with me, with pleasure. But let's say that people are people, basically. That's the reason.
So on that note, we'll finish. Thanks very much.